Welcome to our second video on t-tests and hypothesis testing. In this video, we take up two kinds of t-tests, the independent samples t-test and the related paired or matched samples t-test. First, we're going to look at a couple of illustrations from Module 19 to help us understand what this two-sample test is about. The first diagram, figure 19.1, shows us the research hypothesis. In other words, this is what we think the real world is like, and we're going to try to see if our data supports it. We can tell this is about a population because each of the curves in this chart use the Greek letter mu, which is a population parameter. And what we're seeing in this chart is the distribution of two groups of people. One of them received medication for depression, the other one received counseling, and the means are different. We can see that the peaks for each of those two curves come out at different places, and this gap between the two means is what shows up in the numerator of our t-statistic. It's looking at the larger of the two means usually minus the smaller of the two means. So our research hypothesis is saying that the population would have means that were different from each other and without a great deal of overlap of the two curves. The null hypothesis, still dealing with the population, is shown in the second curve, figure 19.1. And here, both of the curves are shown almost overlapping each other. The dotted curve is the one for medication, and the solid line is for counseling. And the null hypothesis is that there really is no difference between these two groups, that regardless of getting one or the other treatment, the outcome will be about the same. We see this with the means overlapping at the center point. In our two-sample test, we have a different form of the standard error. Rather than being related just to the standard deviation in the sample, now we have two samples to deal with. And in both Module 20 and 21, there were some equations that came up. We're dealing with some form of the standard error being based on the variance inside each of the two samples. One of the key issues is whether the samples have relatively similar variances. If not, an adjusted equation is going to be needed. In this course, we are not going to compute these t-tests by hand. We will use Excel functions to carry out the test. One of those functions does test for the equality of variances. So our goal is to understand the equations and what they're doing, but not necessarily to carry out the computations by hand. Let's look at our equation for the two-sample t-test. It looks a bit daunting when we see this equation, but if we just take it apart piece by piece, we'll see that it makes quite a bit of sense. Notice that the numerator has two parts, one that deals with the population's parameters and one that deals with the sample means. So if you remember, our null hypothesis showed the two means for the population. This is what we're hypothesizing about. The null hypothesis showed them completely overlapping, so the difference that we hypothesize between them is 0. So we're looking to see if the difference between the two sample means is different from 0. We do it by subtracting that 0. So practically speaking, it's only this part, the difference of the two means in the samples, that we'll actually be computing. And then down here on the bottom, we have the standard error of the difference of two means. And our textbook will give us a couple of different equations for calculating it, depending on whether our sample sizes are equal or unequal. When we carry out the 4 steps of our hypothesis test, first we state the hypotheses, Then we determine a critical region, usually 0.05, but it can vary. Then we compute our test statistic, which is what we saw how to do on the last slide. And finally, we have to make a decision. There's two ways we can go about making this decision. In the textbook, we're shown the actual t-value and then encouraged to compare it to a critical value that we find in the textbook table that's at the end of the textbook. When we use Excel, rather than comparing to a critical value of t, which shows up on this axis, we'll show instead the p-value, which is the area beyond our actual t, which represents what's the probability of getting a t result that extreme or more extreme. We'll compare that p-value to the Greek letter alpha, usually 0.05, that we've used in creating our rejection region. Whenever p is less than alpha, that would be when we reject the null hypothesis. What happens when our t-test has two samples and the samples are not equal sizes? Well, first, the numerator of our t-statistic is going to remain the same because we're comparing those two means no matter what we know about the variances. But we do have the possibility that we might need to pool and average the variance because it's not the same in both samples. So the formula for the standard error changes. That's in the denominator or the lower part of the t-test equation. And the standard adjustment for unequal sample size takes the sum of squares within each of the two samples and adds them together, and then divides that total by basically the degrees of freedom for the entire test, the two means that we compute minus 2, and then that whole thing, when we multiply by 1 over n with a subscript of 1 and 1 over n2, it's the same thing as dividing by those numbers. So just as we've done before where we had a standard error that had something about variability on the top and something about sample size on the bottom, and we could take the square root of it, we're doing the same thing, but we're having to take our variability separately for each of the two samples that we're dealing with. Once we substitute in that new equation for the standard error, then everything else about the hypothesis test proceeds exactly as it has in the past. Once you've calculated the t-value, you go on to compare the t-value to a critical value from the table, or if you're working with Excel, to compute the p-value, the probability of getting a t that large or larger. When we compute that two-sample t, the logic that we use to make our decision remains exactly the same. We find a rejection region by looking at the critical values in the table in the back of the book, and then we compare our actual computed t to the critical value. So if our computed t is greater than the critical value, it lets us know that our p-value is going to be less than alpha, and either of those situations tells us to reject our null hypothesis. Now we're ready to go on and look at the second kind of t-test that we had in this week's study. The related sample t-test goes by a variety of names. It's sometimes called a paired or matched sample t-test. There's sometimes that it's called a repeated measures. The basic idea is that the variability between the two samples is going to be reduced either because we use the same exact people in both conditions, that's the repeated measures test, or else we've matched somebody in the treatment group with somebody in the control group on a variety of relevant factors, and so there's less difference between the two groups. The reduced variability in our related samples t-test makes it easier to detect subtle effects because each person or each member of the pair is serving as a control for their own data. Our textbook gives us a very strange equation for the denominator of the related sample t-test. The most common procedure is simply to compute the difference score for each pair of scores in the data. So for instance, if I had a pain value before knee surgery and a pain value 3 months after knee surgery to see if the surgery was actually improving student pain, I would compute one difference score for each person rather than keeping all of their time 1 and their time 2 data, unless I was working with Excel. When we create that deviation score for each individual with their 2 measurements, we can use all of the features of a one sample t-test to create the standard error, estimated standard error in the denominator, and that's what I would suggest doing should it be that you ever have to do this by hand. Our textbook has chosen to show extreme value situations for most of the examples. So when we look at these curves and they're showing us our actual t-value or our actual estimated standard error, it's showing us situations that are pretty far in the tails. But it's important to realize that in much medical and social science data, we in fact never see values that are that extreme. Often the null hypothesis is true. A new drug or treatment may be tried and found not to have any effect whatsoever. So do recognize that many of your t statistics, when you compute them, are going to come into this central part of the curve. Finally, let's look just a little bit about a situation with a type 1 error, what it's saying about the population, and then what our samples actually look like. In this upper of the 2 graphs here, we again see the situation for the population as being one where both the medication and the counseling groups have overlapping curves. So that's indicating that this is what the null hypothesis would be saying, that the 2 groups of people really did not differ from each other. And when we're looking at the type 1 error, it means that we're hypothesizing that that really was true in the population, and somehow we still got sample means that had a fair amount of difference between them. That just by random chance we got one that was quite a bit higher and one that was quite a bit lower. This would lead us to reject our null hypothesis, because of course we don't know this underlying population situation. We only know our sample data, and so because we only know our sample data, we would end up in this case making a type 1 error. In contrast, if we look at the other graph, this is the situation where in the population the curves really are different from each other. So there is a gap inside the population that shows up as a gap of our 2 samples. In this situation, we would also reject the null hypothesis, and this time we would have been accurate when we do so. So this is just a good way of looking at what could be going on in the population when we get these 2 samples that are quite different from each other. And the logic of inference is telling us that this situation where I reject the null hypothesis falsely is going to happen a small number of times. I pick it the number of times, and if I'm going to pick the standard 0.05, it means that 5% or 1 in 20 times I'm probably making a type 1 error, although I won't know exactly which times that occurs. So that's all we have for the complex types of t-tests. The 3rd video in this series looks at effect size and writing up reports.